Greetings, everybody. I am so blessed and privileged to have Dr. Russell Humphreys here to help me understand the paper and also help me get through some cobwebs out of my head on electromagnetic theory. I've been going through all of the basic operators recently. So, given that this is I published in biology, and I got to tell you, biology is so much easier, at least today's biology, than doing physics. At some point,
I would have said just the reverse.
well, I
I
think,
mean,
well, yeah,
I pull out a the journal Nature, for example, and I spend many minutes just trying to decipher the titles. So,
well, having been in both fields, I'll tell you the way biology is taught now is actually easier. But God created something very complex in biology. Decades from now, if the Lord tarries, biology could get very hard because now there's to really understand biology, we're starting to add a lot of physics to it, and it's getting really brutal. I was seeing Hamiltonians and Poisson brackets on some of the last stuff I've seen in biophysics. I'm just like, this is rough. So with that, Dr. Humphreys, could you take us before God's throne? Because we need prayer to understand. I need prayer, and the viewers need prayer to understand this. It's a really important topic. I would be blessed, sir.
well, Father, I really need to understand all this stuff too. So we ask for you to give us your clear mind, Holy Spirit, and just make us uh, know the things you want us to understand and do and think and be and say. And just teach us today, and you make we're asking that you facilitate this, that you make it go smoothly and direct the conversation. So we're asking in Jesus Christ's name, amen.
Amen. So just so I don't scare all the viewers off from the first 5 minutes, it's going to progressively get more technical. But I think the geomagnetic argument for young Earth is very powerful. I looked at Wikipedia, and they said the Earth's magnetic field is going to decay in 1600 years, which surprised me. And I'm going to show you something that I think corresponds to a diagram in your paper. And let me put it up here. Let's see. So this is the strength of the axial dipole
Mm-hmm.
and measurement from 1900 down to the year 2000. This is all inferred here, but I think these are relatively direct measurements. And that seems to correspond to a diagram in your paper. See if I can find it. I saw a diagram this one.
Yes.
Is that kind of this? Is that the same segment?
No, this is the last 100 years or so of it.
Okay.
That segment was 400 years or so.
Okay. So I'm sorry. So we have the blue segment.
The blue segment pretty well corresponds to mine.
Okay.
Yeah. So.
Right. That's a very basic one. So just kind of a pointed question here. In this Wikipedia entry, and because I just want to boil this down at the simple level, and we're going to get increasingly technical here. It says here, at this rate, the direction and intensity of the dipole change over time. Over the last 2 centuries, the dipole strength has been decreasing at a rate of about 6.3% per century. At this rate of decrease, the field would be negligible in about 1600 years. So that's the Wikipedia figure for when kind of the world starts to end. What figure do you have? Do you have a figure? Does that agree with?
I don't know if you can hear my kitty cat. She wants to join the conversation. So.
Oh,
But I think she'll calm down. It's not food time yet, Miss Cat. So let's see. What were you asking?
So Wikipedia is saying that the magnetic field is going to decay, is going to be gone in 1600 years. I mean,
Well,
this is kind of like, this is like kind of as mainstream as it gets as far as popular science.
so
Does that agree kind of with, and you kind of see it from this graph here?
well, show my graph again.
Okay.
Now, imagine a red line going through the center of that graph, through the center of all those points. So some of these points here would be below the line, and these points would be above the line. But the straight line would be an exponential curve on this. This is a logarithmic graph. The
Oh,
scale is logarithmic. And
I didn't
so,
realize that. Okay, thank you.
and by the way, this is real data from the International Geomagnetic Reference Field data. These are actual measurements, and the error bars on the measurement are about the size of those dots, very tiny. So they're very accurate. So I guess my point is that this fits an exponential plus a sine curve, a sine wave curve. So it's an exponential decay with just a little sine wave wiggle on it. And so if it's truly exponential, then it will never die away. It will just fade at a certain percentage every year on forever. So it's not linear. It's not a straight line on a linear graph. It's only a straight line on a
Right.
logarithmic graph. You see what I'm saying? So it's really stretching things a bit to say that the field will be gone in 1600 years.
Well,
So
electrical
it'll
engineering.
just, actually what your reference said, the field will be negligible. So actually, I think the decay time is exponential of the exponential part.
Let me see. That would be equation. I have it here. Like I called. That's the. You know what we call it in electrical engineering. In electrical
Time
engineering,
constant.
right?
We call
Electrical
it a time
engineering.
constant.
If you have 5 time constants, is we classify it as 0. That's just
Oh,
kind of the convention. 5
okay.
time constant. So 5 time constant cycles. And
Well,
the quote.
one time constant of the curve that I fit there was 1600 years. So it'll be about one time constant lower in 1600 years, or about a third of what it is now.
Okay, so I'll multiply that figure by 5. That would be 8,000 years. 8,000 years.
95,000,
My math is off.
close to 10,000.
Okay.
So,
Okay. So just like General MacArthur said, a good soldier never dies; he just fades away. So an
yeah,
exponential curve
yeah.
never dies; it just fades away.
But the issue is important because as when you were in electrical engineering, Sal.
Electrical engineering, my undergrad, and then physics, my grad.
Okay, well,
I'm a disgrace to my degrees because I've forgotten so much at this point.
so you know what a circuit with a voltage source, or maybe closed, no voltage source, but it's got a current in it, and you have an inductor in series with a resistor, and the time constant is L over R. That's exactly what's going on in the Earth's core, I think. You have you have a loop of current going around from east to west. That's the direction of the current. And that's going through a material which is resistive. It's not a perfect conductor. So it has a certain resistance. So the L over R time constant according to this graph and this fit, is about 1,600 years.
Okay, so
And this is the exact way to calculate the time constant. But you could also estimate how much the inductance of the big current loop was. It's a certain size, and you can estimate what the cross-sectional resistance would be, and divide the one by the other, and you get about the same answer as this. But this is the exact answer. This starts with the guy who derived this, Dr. Thomas Barnes, and before him, a fellow named Harold Lamb in the 19th century. All he did was solve the Maxwell equations for this situation of a loop of current going in the core.
Okay, I really appreciate that, because I'm trying to popularize some of this. In the fact that Wikipedia had said that the magnetic field is going to decay in 1,600 years, I can qualify that and say, according to our calculations, it's longer than that if we use the 5-time constant rule. It never goes to zero; it just fades away like general.
No, so with the data we have over the last century, you can't. There's not much difference between a linear decrease and an exponential decrease. It's just too short a
sample size. Yeah.
Now the data we have going back, have you heard of archaeomagnetic data? That's the magnetization of artifacts, like a brick in a kiln that last got heated on a certain date, and it preserved the magnetic field. That's archaeomagnetic data.
Archaeomagnetic.
Archaeo.
Magnetic. Okay.
So that's
this is great. How far does that go back?
So the archaeomagnetic data is rougher. It's like got about a 10 or 20% error bars around it, but it shows the exponential decline going back about 1,000 years, and then it starts to round over as you go back in time, and it reaches a maximum about the time of Christ. Then it goes down, and then it bounces up and down quite a bit as we get back toward the time of the Genesis flood. The field was more chaotic, right after the flood, and it took a while. It took about 2,000 years for those disturbances to die down and settle down. So then it rounded over about the time of Christ, and then it settled down to a nice smooth exponential decay about 1,000 years ago, as far as I can tell from the data.
And so just to put you on the spot here, greetings, Ben Rex. Ben Rex is a graduate student in electrical engineering in photonics, and he doesn't do a lot of. He told me he doesn't do a lot of Maxwell's equations. Every electrical engineer has a specialty. Some of us just do circuits. Some of us do just like computer stuff. But this is great. So we have an audience of electrical engineers, computer scientists.
Yep.
One works on a particle accelerator. So I had a whole bunch of questions.
Oh,
some
ask
of them
away.
are trivially basic. So we have conductance in Siemens. So 33,000 Siemens is 1 over 33,000 ohms. I mean, that's a really tiny. I'm used to dealing with 1,000K resistors.
It's 32,000 1 over ohms.
So that, okay.
They used to call it a mho, M-H-O, like ohm backwards, but now it's a Siemens.
Okay. Okay. So we're talking about a very conductive. I mean, this is like a wire. I mean, I usually don't use resistance on a wire. It's so low. So when I was just seeing these numbers, I wanted to confirm that I'm reading it right. That's like no resistance at all. We consider that a conductor.
Well, no, people have, yeah, it's about like the resistance uh, of carbon in a carbon resistor. Uh, I believe. Let me. No, it's more than that. It's about like the conductance of iron at normal temperature and pressure.
Okay, so it is a conductor.
But people have done calculations on the conductance of iron at the temperatures and pressures in the core.
Okay, that's what I wanted to okay, I just, sometimes when the numbers jump out at me, it's like I have to make sure that
That
I'm getting
you didn't drop a zero somewhere. Yeah. So,
exactly.
but the
So,
in the so the ohmic conductance in the core, ohmic resistivity or ohmic conductance in the core should be about 300,000, 200,000 or so moles or Siemens. But the decay constant is showing a lesser conductivity, about a factor of 10 less than that. So you with me so far?
yes, yes,
Okay.
and I saw that in your paper, and then I have just a question about this equation
But,
here.
but let me make my point.
Oh, sure, certainly.
Ohmic resistivity is not the only resistivity to worry about when we have turbulence in the core. And you have a thing called turbulent resistivity, which let me switch to conductance. The turbulent conductance is a lot less than the ohmic conductance. So I think the 30,000 Siemens that the curves are showing is turbulent conductance, or the inverse of turbulent resistivity. So the roiling and boiling of, it's very slow, but it's large, and a lot of it adds another factor to the resistance, and so that comes from people who've studied the conductance and resistivity of plasmas, and they discovered this turbulent effect. So, okay, now I derailed you from some other questions, so go ahead.
So my understanding is, well, just to revisit the point, since I did read it in the paper, if we didn't have the turbulence, it would conduct better. With the turbulence, it doesn't conduct as well. Okay.
Right, you got it.
This is very helpful because as I try to popularize kind of creationist theory on geomagnetism, this is also great because I can relate it to that Wikipedia article. They said 1,600 years. We'll give them up to 10,000, but it's going to be low, and that's a testable prediction. We don't have a lot of testable predictions like that in creationism. This is one of them. That's why I was excited. And then I'll point out to the viewers, we're getting some good results for the planetary magnetism too.
Right.
So, all right. So now I'm going to cover this part here, equation 3, and I sort of understand this, but okay, I'm going to ask some really, and you may have covered this.
Let me take a look at that equation again. I got
sure.
equation 2, but I didn't. Let's see. Okay. What is A naught? Oh, okay. Yeah. A naught goes into equation 2 for the current in the core. So a perfect dipole field coming from a current in the core would have that kind of behavior with, let's see, theta is the latitude, and what is x? Oh, x is just the radius reduced by a factor. Okay. So, okay. Yep. Catching up to myself here. Go ahead.
Oh, don't. I tell you, I've written some papers. I don't even remember what I wrote in the math. I'm just like, oh my goodness. And I'm the author of the paper. So
Yeah.
I've experienced that myself too. Okay. So, and you may have covered this before, we are so pressed for time. So I have this, this is a model of the earth, obviously. And now I'm going to ask something really basic. So this, inside we have the core,
Yeah.
which I can't
About
really open.
halfway down, the fluid core starts, halfway down in radius. So, yeah, go ahead.
Okay. So for lack of having anything better than this
Oh,
is
that's
not,
a good toroid. So go ahead.
so do we have like basically a sphere, and then we have um, the sphere turning inside, that this hot molten sphere, is that their model? Uh,
No, the toroid, that's within this spherical conductor, hot molten, mostly iron, uh, is spherical conductor. But within it is flowing this approximately toroidal current, electric current. So that's electrons flowing in the core. It's not a mechanical motion of the core.
okay. I'm really glad you're here now because I did not.
You're an electrical engineer. You should know it's current. So, yeah.
Okay, so this is, it's okay. And I'm going to ask you another dumb question. And greetings, Mark O'Connell. See, you're very revered and popular. And then Rebecca's here. All
Oh,
right. So I'm going to have to ask some dumb questions again. All right. If you have, this is going to be even more basic. And I'm embarrassing myself in terms of electrical engineering. If we have like a pipe and you're pumping ions through the pipe,
mhm.
just like, say, a charged fluid with lots of ions, I would presume you'd get a magnetic field um, around the direction of the flow. You get these kind of circular.
Well, that depends on what the electrons are doing. If
Really?
if the electrons are moving along with the positive ions, the net charge is zero, so there is no electrical current flowing along in the pipe. You would have to have the electrons flowing one way and the ions flowing another for them not to cancel their magnetic fields out.
Okay. All right. I'm glad you told me that. Didn't know some basic physics. So even if we had like a charged ion, and okay, so the Earth is rotating,
Mhm.
that's not going to generate a magnetic field just because it's rotating.
Nope, it won't.
Okay. I'm really sorry to ask you these questions, but
No, no, I think you're asking questions that a lot of people have to learn, and I had to learn them a long time ago. So, so when I first started looking at it, so
here you got a fan here. You got two fans. You got
Rebecca Davis,
everyone here, and these are just live fans. There's probably going to be,
you have
people
dead
watch
fans too?
record.
No, you have fans somewhere else. Yeah, that will watch us later.
Yes,
So
that's
go
what I
ahead.
meant.
Okay.
Okay, I'm really, thank you. And I was telling everybody, one reason I do these streams is one way to learn something is to try to teach it. In the
Yeah.
process of trying to review your paper and teach it, I realized there's so much I didn't understand. Yeah, it's not late fans, it's later fans. Good one.
Okay.
Later fans. So as I tried to teach it, I said, this is so much I don't understand, even going back to my basic physics. And so now, what if I get the theory, the dynamo theory is proposing a toroidal current? Is that is
Uh,
that the mainstream theory, a toroidal or a net toroidal current?
They are actually kind of vague about that, but I think in order to have a dipole field outside the core, which we see, you have to have some toroidal current there. So you have to. So it's mostly a toroidal current, but there's, in their view, there's a lot of fluctuations and different variations in the shape of the current, and so.
So I'm going to take then. I'm going to imagine this is a model of the toroid inside the core.
Yeah.
And you're saying electrons are flowing in east to west. So that would be east.
So the electrons are flowing east to west.
Like this. So if we went to the inside.
I'm sorry. It's the positive. There's a convention electrical engineers have.
Oh yeah, positive charges.
Currents.
Positive charges moving east to west. But
so we would say the current, meaning where positive charge would go, is east to west.
But the actual electrons are going west to east.
Yeah.
Okay.
Probably there's both. There's probably ions slowly moving westward, and electrons more rapidly moving eastward. So it's probably both.
Okay, this is good. I don't know how the electrical engineers adopted positive charges, but that's okay. It works well in solid state where we have electrons.
Go back and blame that on Benjamin Franklin. He decided to label one part of his static charge generator positive and the other part negative, and so it's stuck with us ever since. So.
Okay, so we'll go with positive. Okay, guys out there, you heard it. We're adopting a convention of positive charges. Okay. The electrical engineers totally know this, even when physically it could be electrons going the other way. It's just the convention. Yep. In fact, it's embedded in electrical engineering literature, and I believe it's probably in electromagnetic theory literature. So
it's there.
All right. So the positive charge is going east to. I'm sorry.
From east to west.
East to west. On my globe, this is east to west, like that. Yep. And it's inside the core.
Yep.
And I got to tell you, that just seems kind of strange just to begin with.
What's strange about it?
Where do you get all the energy to do that? And how does it sustain? And that's why I was beginning to look at this. I could see why we would think that this toroidal model is, I don't know how it could be sustained for millions of years. That's just my intuitive look.
Oh, I think so too. But the dynamo theorists have been working for over a century to find out some way to have a generator action within the core with fluids flowing through magnetic fields and so on and so forth. And that's the old British name for generator is dynamo. So it was a Brit who first started it back in 1919, and so it got called the dynamo theory. But they've been working hard since I think it's 1919 to try to make some kind of theory actually work, and they haven't been having much success. So
okay, so then all right, so then we have, okay, I really wanted to understand what the meaning of this diagram was.
Yeah.
And so now I see it. We have this, we have the electrons moving.
Or the positive
charge. Thank you. I'm gonna get so confused. It's the positive charge.
Okay. But that's the current. The current that you EEs always talk about, and what the physicists also talk about current in the same way. So
that makes it better. And it's really funny. The United States Navy temporarily tried to do it the other way.
They did.
And my electronics teacher was trying to do it that way, and it didn't agree with anything I did anywhere else.
So yeah.
So so the current. Thank you for correcting me on that. So as the current moves in that direction, and I remember this from.
Can you see my cursor?
No, I cannot see your cursor.
Oh, I can only see my cursor. Well, you see that that arrow that's labeled 90% pointing to a contour right near
Here,
the
I'll
center.
move there.
So uh, those contours drop off 10% in the current density. That's the amperes per square meter that's actually flowing. And actually, it's milliamperes per square meter because there's a lot of square meters there. But 10% of all the current is flowing in that uh, innermost contour. And then the next contour, 20% of all the current. So you see that sort of gives you a feel for these nested contours give you a feel for the actual shape of the current that's flowing.
I got to tell you, this looks kind of just like, I'm sorry to be a little skeptical here, but that means at the center you don't have very much. You have it kind of here.
Oh, no, no, no. Well, at the center, yes, you have, at the very center, you have a contour that has all of the current within it, but that contour is as big as the whole core. So, so, but most of the current is flowing in that more central location. That's what the contours are telling you.
All right, I'm going to have to look at that. And then I got something from our last talk that, so the current is going east to west,
Mm-hmm.
and then the field line would go like that from the South Pole to the North.
Right,
Okay.
right.
All right.
So the arrows on the field line at the North Pole are pointing into the Earth.
Okay. All right. Oh, and it was right here. So I presume this is the north?
Yes, that's the North.
And so, okay, here are the field lines going through then. Okay.
Mm-hmm. Yeah.
And then right here this is like the 90% current region.
That is field there. That's not current. The current is a little out there, and right where your arrow is a practically no magnetic field and this. See, this is a calculation based on the assumption that it's purely a dipole, and it's purely a dipole inside the core as well as out. That's the assumption. And then this is just a calculation from Maxwell's equations. So,
okay, this is great. You have helped me enormously already. This is, boy, getting through all the little questions first. So we reviewed the equation of the R over L, the time constant.
L over R is the time
L over
constant.
R. Okay, I'm sorry.
The inductance, I think it works out to be about, it's either 1 or 5 henries. So you have you have the total resistance is down in the micro ohms, the total resistance of the core, or if I recall right.
Most of the time constants I've worked with are capacitors. So RC time constants,
Yeah,
so R times
right,
C,
right.
because a lot of the integrated circuits don't even use inductance.
They don't use inductances. Yeah.
No, and unless you're modeling
that's
physics.
to their great loss. They should have more fun with inductance. So back in my ham radio and radio broadcasting days, we depended very much on inductances. There were coils all over the place. And so.
Oh wow! See, you have another fan here. Good clarifications for me as well. I'm a bit rusty on some of this. Got to go to work soon. He's in Australia. Thank you, Peter. He had also studied electromagnetic theory some time ago, and so we're all relearning this.
Yeah, I kept my handiness with electromagnetic theory because first I worked for General Electric and doing lots of electromagnetic stuff, and then I did lots of electromagnetic stuff for San national laboratories, all sorts of electromagnetic stuff. Some really big circuits that when they're fired, they shake the ground. but there's big capacitors and high voltages and mega amperes of current and megavolts of voltage, and so I kind of kept up to speed on Maxwell's equations and everything about them. So
Oh,
for me, it's like just plain fun. So.
This is great. I was telling the viewers, I said, when we're going through school, I ought to be lucky to have 2 hours total interaction with the professor through the whole, because he has so many students.
Yeah.
So this is gold that I have someone I can kind of ask all these questions.
That gets a little better when you're a grad student, because then the classes are smaller and you
Yes.
have your own major professor you can pester all the time. And
so. My grad school had a lot of students in some classes, except for statistical mechanics. There were only 4 students.
I can understand that. That's why they called it sadistical mechanics, right? Have you never heard that?
No, I never heard that. But there was this story. I mean, it's a sad story. They said, Boltzmann, the founder of statistical mechanics,
committed suicide. Yeah.
Ehrenfest committed suicide. Now it's our turn to study statistical mechanics.
Yeah. So.
Oh boy, we can. This is nerd fun here. So okay, so now we've gone through so many of my questions so fast. I mean, like I was like, see, we got through this one here, and then he explained it's your calculation 1,600 years for a for one time cycle. Okay, so now let's see. So now I know that it's not the liquid moving. So according to this,
well, the liquid moving has an effect on the magnetic field. So in figure 10 there that you're showing, the arrows pointing to differential rotation are pointing to the actual fluid rotating faster westward at the equator than it does at the poles, and that twists the magnetic field lines.
See, now this is where I was confused. So we have the electron, the current, the positive charge is moving east to west, but then in addition to that, we have the fluid at the equator moving a little bit too. Okay.
Right.
See now, and
so
that affects.
We're distorting it from a nice dipole field all of a sudden. So we had that nice dipole field, and now we turn on differential rotation, and we twist magnetic lines of force.
Okay. And so that led to this question here. So let me make this a little bigger. Hang on. I'm trying to make this a little bigger so I could show the equation that of interest here. Okay, so we have this thing called a toroidal. So this is the time constant for the T is the time constant?
Yes. So yes, yeah, right.
It's just like equation 5, like the L over R.
Yeah, the bottom one is like L over R. That's for a toroidal current. But then the current that generates a toroidal field decays in a different way. It decays about twice as fast. If whatever you've had toroidal inductors, you had if you had a toroidal magnetic core, and you wrapped your wire around the core toroidally, then the current that's in the magnetic core would be toroidal. It would go around along the axis the I don't know what you would call it, but it would go along within the core all the way around it. Yeah, like that. That's good.
Okay.
So
So
that
there's a toroidal field,
and
which,
yeah.
so this is funny. Okay, so if I may just, let me make sure I'm getting the geometry right. So we have a toroidal current that goes
Mm-hmm.
positive charges going east to west like that,
Mm-hmm. Mm-hmm.
and that creates a dipole field.
Right.
Okay, now it's starting to make sense.
So
And then
then,
we have this toroidal current that generates.
yeah,
Uh,
that's right.
we have this other kind of current that generates a toroidal field, which is
Yeah.
inside that goes
Yeah.
kind of. Is that
Right.
correct?
That's right. And only it's not. It's more the magnetic lines of force being distorted and pulled in a toroidal direction. So you take your dipole magnetic lines of force and you add a toroidal magnetic field to get the resultant, which is this twisted looking magnetic field.
Okay.
And so it's the twisting of those magnetic lines of force that generates the current around the toroid, the electric current that's going around the. So
So that's what's causing this little shear here. The toroidal field is causing this bend. I'm sorry. I'm sorry.
I'm not
Hang
seeing
on.
it. I'm
Can't
not
see it.
seeing what.
I'm
Okay.
sorry.
Yes. Yeah.
So the toroidal field is causing this bend here.
Oh, yeah. What's causing it is the fluid grabbing the magnetic lines of force and twisting them, and they're moving faster in the westward direction at the equator than they are at the pole. So they get twisted. You see. So imagine rubber bands, and they're embedded in a liquid which has pretty much got a hold of them, and the liquid moves, so the rubber bands twist into that shape. But when they twist into that shape, then there's some uh, a toroidal current going around in there that you can't see, that's maintaining uh, the. I'm sorry. It's I guess.
I don't know if we kind of call this kind of current that circulates.
I think you call it poloidal because yeah,
Poloidal.
yeah. So a poloidal current generates a toroidal magnetic field. So,
Okay. I'm sorry, I overspoke you. A poloidal current creates a toroidal field.
right,
The toroidal field creates a dipole magnetic
right.
field. Okay, that's
You got it.
this is where this is where everything has. Um, if I'm
By the
not,
way, you don't put the I in the I. You have IAL at the end. It's just AL, toroidal, poloidal, not
poloidal,
toroidal. It's
toroidal.
tor.
So
It's toroidal.
a toroidal east-west current creates a dipole
Yes,
field. A poloidal
right,
current creates a toroidal field,
right.
and
I
that's
imagine
illustrated.
everybody is totally confused by now. So
Okay, so the current flowing here would be called poloidal,
poloidal. Yep.
and then what if we could kind of visualize it? We would have the magnetic field kind of circulating inside the little
Right.
donut.
Well, that's exactly how I visualize it. And if you have a magnetic core and that little donut is magnetic material, then you have a whole lot of magnetic field, mostly in that core.
All
Very,
right.
very little of it gets out of the core. So,
And I think the reason we do that is so you can make you could have an inductor with more Henrys.
right. That's
Okay,
exactly right.
goodness. All right. That's some of the old cobwebs of electrical engineering. And I do know, like inside your car, you have all these field windings. And then when you like break the circuit, you get this tremendous spark, and that's how you get the
Yes,
spark plug. Okay.
I really got a strong feel for that one time when I took an ohmmeter and tried to measure the resistance of one of General Electric's huge power transformers.
Oh no, you don't do that.
Many Henrys. So the needle kept moving up slowly, which meant that more and more current was flowing through the big transformer core. And then I got tired of that, and so I just lifted the one of the probes of the ohmmeter off the electrodes, and a big arc followed that. Because the current didn't want to stop flowing in an inductor. It's so.
Oh boy.
Actually, that didn't happen to me, but it's vivid in my mind because it happened to a technician at General Electric. So, but anyhow.
I wonder if it didn't bust the ohmmeter, I hope.
Oh, it sure did. So,
I shouldn't laugh. Okay.
I think it did. I don't know. So.
Oh, okay. So earlier, about between 1 p.m. and about 2:30, we were reviewing this passage in the paper, and I was saying I need someone that this could take me years to figure out. If someone could just, I could have this conversation. You've just literally saved
I'm
me.
giving you a jump start. Okay, yeah.
Absolutely, because
all right, my pleasure. I like doing it.
This is going to be a great service then. All right, so now I feel like I'm actually reading your paper with comprehension. And this is
By the
so
way,
far a lot of I'm sorry.
This twisting effect actually is observed in the sun. The sun, they have ways of looking at the magnetic field in the surface of the sun. They have ways they can determine the strength and direction of the magnetic field. And they see every solar cycle. The twisting goes in the other direction, by the way, but they will see after 2 or 3 years into the sunspot cycle, they will see the magnetic lines of force twisted all the way around the sun, several times, and then it goes. The field goes through a reversal on the sun, and it starts unwinding, and then reverses itself, and then starts winding up in the other direction, and so on and so forth. So, so this is a we have no way of looking at the exact structure of the field lines in the core, but it's a pretty good guess that it's doing pretty much this what I show here, because we see it in the sun. So.
And as far as I could tell, a lot of what's being already described in the paper, there's a lot of mainstream stuff here. This isn't just.
Oh yeah.
This is colloidal is a that is a mainstream term. That's not something we're making up. And I've seen it in Wikipedia. It referred to this the 0.2 degrees per year westward drift, and that's a mainstream. Let's see. Yeah, right here. It says here 0.2 degrees, a westward drift of a rate of about 0.2 degrees, prominent non-dipolar part of the secular variation.
Yeah.
Okay, so this is good to compare what mainstream theory is versus, creationist theory, and there's so much that is in common, which is great.
Well, and in fact, I don't think there's anything in the paper that's not standard electromagnetic theory. It's just nobody has ever put it together to test the dynamo theory. So.
All right, so I think I'm almost through most of my questions. That was the biggest hang up.
Okay.
Okay, so now I also had a question on equation 4a. Let me see that. So.
Oh, okay.
So this is the strength of the magnetic field. So the way I look at it is Let me see if I could describe the way I interpreted what that equation meant.
Well, there's two equations. One is the radial magnetic field going, outward from the core. The other is the theta component, or the latitudinal or the poloidal component, I guess. So,
and the way that I interpreted this, and please correct me if I'm wrong, is that hang on, I'm sorry, I'm just scrambling here. I could take equation 4.
Yes, if you plot out equation 4 and turn it into where the lines of force are, you would get that picture there.
Okay, that's what I wanted to confirm, because I told that to the viewers and I said, I hope I'm right.
Yep,
That I could take this equation and I could generate kind of a diagram like this.
Right.
Okay, great. All right, that's what I wanted to confirm. This is so helpful. This is immensely helpful. Okay, so now I know the difference between a dipole field and a toroidal field. And then I have equation 9. Russ, you saved me months of work. I thank you. Okay. Because I feel this. I mean, just if you could share your thoughts here, see if it agrees. I think this is I personally think this is a very strong case for a young solar system and a young Earth. The magnetic field things. It's also a very testable hypothesis that we can do in real time. In my lifetime, I think the magnetic field of the Earth has decayed about, looking at the graphs we saw at the beginning of our show, probably about 3.6%. That's a lot.
Yeah. Yeah, it was six something percent. So
6% per century. I'm not that old.
Right.
So I had equation 9, and okay, I have a question on equation 9 here. Just a matter of, are the brackets an average or an expected value? I've seen that notation in quantum mechanics.
Yes, it is.
An average?
And if you have an average, when you have, eddies, when you have turbulence, you have lots of different velocities and rotations at every point. So you can average over a volume, and you get the average. So.
Okay, so that's the average, and so this is it's a dot product, so that ends up a scalar. Okay, I got you.
Yeah.
And there is one. I'm sorry.
No, go ahead.
So there was another passage here. We're not going to go through all the whole paper today, obviously, but this is as far as I got, and I'm glad.
By the way, what you were showing, that equation, that is this thing called mean field electromagnetics. This equation up here.
Equation 8?
Equation 8. I'm sorry, you can't see my finger. Not that well. So that's the electric field in the phi direction, in the east-west direction. All of those quantities are actually the phi component of ease. I think I probably said that up there, but so the electric field that's generated depends on this alpha effect times the magnetic field that's in the phi direction, and then another, that beta is the turbulent part. It's the inverse of resistivity. It's the turbulent conductivity. And so those two components are fighting each other. And this is all a result of what Cowling had a really nice explanation of this this theory. And this is really kind of the heart of the dynamo theory right here, equation 8. So, but the first term, alpha times B, it generates the electric field or the current. The current, the electric field then makes current. And beta times the cross product, del cross B, that's a resistive effect, and they fight each other. And what I am trying to show in the paper later on is that the second term overwhelms the first term for conditions we have in the Earth's core.
Oh, thank
So,
you.
so, there would never, a dynamo couldn't work. What the dynamo theorists want is that first term to be strong and the second term to be weak. So
This is excellent. This is so good. I can't thank you enough. Now, I have more of a very basic question, and it was in turbulent dynamos. All right, this is like a basic. All right, so it says the magnetic induction equation, and then I wanted to see, where did I have it? Wrong slide. I'm sorry. One moment. Is the magnetic induction equation, can it be derived from the third of Maxwell's equations here, or am I way off?
no, that's it.
So
That's
this is the magnetic. Okay, we had some discussion of what is
a changing magnetic field induces an electric field.
okay.
That's how transformers work.
So this is the magnetic induction equation is the third Maxwell equation, the Faraday law of induction.
I think that's what they mean by the, yeah. I have to go back and look to see what Cowling was using it to mean, but I think that's right. So anyhow.
I mean, there are various forms of this, but it was just provident. I was reviewing curls this morning.
Mm-hmm.
So there are two divergence equations and then two equations with curls.
Right.
So, okay. All right. So, all right. So now what I had seen was, and we're almost done here. And this is enough to get me unstuck.
Okay.
So this kinetic theory, kinetic dynamos, large scale core fluid flows that would produce the observed fields. Is this like a thunderstorm inside? Kind of, not exactly, but like when heat hits our atmosphere, it creates all these rotations and motions. Is that what the kinetic?
No. In fact, that's the inverse of the kinetic. The kinetic dynamos are big, large-scale flows of fluid current, and then all that does. And what goes on in a thunderstorm is turbulence, lots of small-scale flows going every which way. That's why the thundercloud boils up and roils and boils. You see it going up, building up. So there's turbulence in it. So, but the kinematic dynamos really can't work, and they prove that now.
So they were trying to invoke huge physical flows of I mean, just so that even though it's disproven, I would like to understand what their idea was. It was a large amount of actual physical fluid motion or heat.
Yeah.
Wow. Okay.
So and Cowling and the successive people who made the anti-dynamo theorems showed that you can't have any simple such flows that are symmetric around the magnetic axis. They can't do that. So you have to have smaller scale flows that aren't symmetric and are just going every which way and doing things through turbulence to accomplish what they want.
So this is, at some point I want to be able to understand this. This is an alternative statement of Cowling's theorem, and there are various versions of Cowling's theorem.
Mm-hmm.
But you have helped me understand. I can now start to read some of this, because some people on the net have been saying Cowling's theorem has been disproven. I'm just like, in this conversation, I'm realizing I don't see how it can be. They may have found some pathological cases in very dispersed, very thin plasmas, but for solid, this looks right.
So what they're saying, they are not saying that there's any mathematical flaw with Cowling's theorem. It's a piece of math, and no one, as far as I know, has ever shown any problem with Cowling's theorem or the other. There's two other big dynamo theorems, anti-dynamo theorems I mentioned in the paper, but no one has ever shown a flaw, mathematical flaw with those, which is what you'd have to do if you were going to disprove Cowling's mathematical theorem. You have to find a mathematical flaw. But what they're saying is look at things like the magnetic field of Saturn. It's almost it's a very good dipole, and the tilt of the magnetic axis of Saturn is within 1 degree of the spin axis of Saturn. So then what the dynamo theorists say, well, assume that Saturn got its field generated by a magnetic field. Assume that a dynamo generated Saturn's magnetic field. Then the fact that the field is axisymmetric, so it's so symmetrical around the spin axis, the fact that it's so symmetric means that all those theorems had to be wrong, that you couldn't, but what they're assuming is that Saturn's magnetic field was generated by a dynamo.
Exactly.
And I am suggesting that no, that's Saturn's primordial magnetic field, the one that God created Saturn with. And I have, I have a theory about how God created those magnetic fields to begin with. So if the primordial field was axisymmetric, a dynamo didn't generate it. So, it has nothing to do with Cowling's theorem about dynamos.
Right. It was circular reasoning.
Yes.
Yes.
They're assuming what they want to prove.
Oh, there's a lot of that in origins theories. Wow. Well, Dr. Humphreys, I can't thank you enough. You see, I realized early on it would not be productive for me to try to read the paper with total misunderstandings. I would never be able to get.
Okay.
So this has been immensely helpful.
You were trained in, you had Maxwell's equations a long time ago, so I'm worried about the poor folks who never had it. So,
Well, we speak to, I have two channels, one for kind of general audiences and then one for specialized audiences here.
But even the specialized audiences, a lot of them aren't familiar with this math and Maxwell's equations and all that.
So I have on my other channel about 1,400 subscribers. This is my academic channel, which does biology and physics.
Mm-hmm.
We get about 4 or 5 visitors on topics like this.
Yeah.
So this is very, very specialized. But the reason that I'm getting involved in this is, as you know, creationism is moving forward quietly in academia. And questions like this are starting to come up. And this is when I was in a debate over the age of the Earth, I noticed my opponent's silence about the geomagnetic field.
Did you ask him about that silence?
No, he changed the subject. He changed the subject, and I didn't recognize the move. I was in a 2 versus 2 debate, and my partner was just he was getting chewed up. He didn't really know what the maneuvers were to change the subject.
Mm-hmm.
And I should have asked him more about the silence. But the reason I bring that up, it was because of his silence. He's a professional geochronologist, does a lot of radiometric dating and et cetera. But when I noticed his silence, I said, I think this could be a good proof for young Earth. I noticed they're silent on things they know are problematic. I said, why don't I learn more about this? And I could feel more comfortable defending it. So just like with Cowling's theorem, that's really powerful. If I can understand the theorem and its implications, it's going to be very powerful, because this is feeling like what people do with Origin of Life. The chemistry never added up to begin with, but they still keep trying to make it work.
Yeah. Well, in my PowerPoint that I think I sent you, did I send you my PowerPoint on this same subject?
I think you did.
Okay.
I was hoping to talk to you first so I could understand a little more.
Okay. Actually, it may be that the PowerPoint will help you understand the paper easier. For some reason, it's easier when somebody actually tries to explain something live to you. So anyhow, there's a little section about Cowling's theorem, and I point out what Cowling pointed out about axisymmetric fields, and then anyhow, it might help you actually better than the paper would. So that's why I sent it. So,
oh, thank you.
So,
all right. Well, I don't know when you've been so generous with your time. I probably will be reviewing electromagnetic theory for over the next several weeks. I also have papers in statistical mechanics. Do you know Dr. Andy McIntosh? Have you heard of him?
Yes, I do. He's a good man. He's a good creationist.
Praise God.
And an engineer, isn't he? He's an engineer, I think. So.
Engineer, physicist. Okay. At some point, applied physics is engineering, so the distinction kind of blurs.
Yeah, that's true.
And his is in thermodynamics, but he doesn't have a lot of statistical mechanics. And I volunteered to help him with Origin of Life and statistical mechanics, thermodynamics. There's something called Landauer's theorem, which is a physics theorem that connects the amount of energy, minimal amount of energy, it's in the electron volts, not very much, required to make 1 bit of chain of information.
I've heard of that. Yeah.
And I can actually see it like when we're making something homochiral. It affects the Gibbs free energy. The Gibbs free energy is favorable to go to the racemic state, and it corresponds to Landauer's theorem.
Right.
And I'm saying this is how we actually can start to connect kind of informational ideas to thermodynamics and statistical mechanics, but in a lot more rigorous way that would pass muster. And I told him, I said, the first thing is you have to talk about it in terms of organization. So why did I tell you all that? I might have to take an operational pause from electromagnetics to work on that paper, plus Dr. John Sanford. We have some things outstanding on genetic entropy. I'm pleased to announce 3 or 4 publications in secular venues just in the last 2 years.
Wow.
In some very good venues, including Springer Nature. And that's just a miracle of God, because we're creationists, and I can't believe the editors didn't toss us.
That's very good.
But I felt this, people have been asking me, what are your arguments for young Earth? I'm like, well, I've never felt we had just killer ones like we do compared to abiogenesis. So when I debate evolutionists, we just kill them on abiogenesis and eukaryotic evolution. But when it comes to the age of the Earth, I'm just like,
genetic entropy is as long as life is supposed to have been on the Earth, it couldn't have survived more than a few hundred generations, regardless of the more complex life, let's say. So that's pretty strong argument for short time scale. So
yes, so and it's a testable prediction. It's predicting, as Jesus said, this world is passing away. Also, human civilization, if he doesn't return, is going to pass away just genetically. And then this geomagnetism is also a decay. And so the young Earth creationists actually have 2 testable predictions that can, if the Lord tarries, in principle, I'm saying in principle, we could have measurements as long as civilization is alive.
You stimulated a random neuron firing here. I've speculated as to whether or not one could show the dynamo theory can't work by appealing to entropy. That you have the dynamo theory has high entropic sorts of energy, like the heat flow in between the core and the mantle. That high energy is supposed to provide the energy to make a magnetic field, but the magnetic field is a low entropy form of energy. It's more organized, and so the dynamo theory shouldn't be able to work by accident. You have to put design into it.
Right.
So I've kind of wondered whether somebody could run with that ball and score a touchdown also. So.
I would prefer to avoid sadistical mechanics if I can. But in regard to the question Andy McIntosh and I are working on, we have to go there and maybe not too hard into it.
Okay.
Yeah, it's an exciting time. There's just so much we're learning about everything, and
yeah,
you're
having fun, and that's just the way it should be for a creationist.
Oh yeah, having too much fun.
So creationists have more fun.
Yes. So it could be a while before I revisit this, because I really need to get some of the basic I want to go through my electromagnetic theory book, and I have one by Griffiths, and just kind of go through the exercises.
Yeah.
And I've learned so much, and I think I want to teach electromagnetic theory, and then, as I go through the paper, I now have hope I can get through the end of the paper and understand most of what was trying to be communicated. Mm-hmm. And I can reference mainstream sources that are actually saying problems with dynamo theory. So
you just feel free to do it on your own time scale, whatever you want. I'll be available, and when you need a little bit of straightening out or clarification, I'll be happy to try to do that. So.
Well, we're about to close the show. After you say the prayer, I'm just going to run the end credits, and you could just leave the studio at that point. I usually just have end credits. So if you could close us out hang on, let me just get my end credits all set up here. All right, Dr. Humphreys, could you bring us before the throne of the Christian God? Thank you.
Father, thank you for guiding the conversation. I think you made it profitable for us, and hope for the audience too. You are doing good things with your people, and especially those who happen to be scientists and creationists also. So please keep on working with us. And we thank you. We give you the glory in the name of Jesus Christ. Amen.
Amen. Well, everybody, take care and God bless you. Okay. Thank you again, Dr. Humphreys.
Thank you.